Are you going to edit this? Because that's going to happen
Yes.
a lot where we don't know who's going to answer.
I'm going to edit.
Yes.
Don't worry about that.
This is Relatively Prime. Objects in the mathematical domain. I am Samuel Hansen.
I am joined here today by Katie Steckles and Peter Rowlett, the creators and hosts of Mathematical Objects, a new podcast from them and the Aperiodical. Somehow it didn't end up connected to Acme Science in any way whatsoever until now. So welcome to Relatively Prime, Katie and Peter.
Hello.
Thank you for having us.
So if you wouldn't mind just letting my listeners know a little bit about what Mathematical Objects is as a podcast.
Well, Peter and I have done a few podcasts in the past. We've done various bits of things through the Aperiodical. We also did a series of podcasts for what was at the time the Further Maths Support Programme, now the Advanced Maths Support Programme, which were about kind of maths careers. And we thought since I just recently started a new job at Sheffield Hallam, where Peter is based, we were going to be in the same place on sort of regular basis for the next few months. We thought we might as well take advantage of that and do another podcast.
So the idea of the podcast is that each episode we take an object and we use that object to have a conversation about some mathematical topic. Usually there are some very obvious ones where you sort of pick the most recent one we released is a noughts and crosses board, and we talked about noughts and crosses in game theory, and that's very directly you can see how that's a mathematical object. There are some that are a little more left field, like a t-shirt or a piece of food or something like that you don't think is mathematical, but it allows us to speak about a mathematical topic.
So mathematics in many ways over the last few hundred years now has gone from being a subject that is more about the physical world to being a subject that in no way has any real ties to the physical world. I mean, I know people who do work in like 127th dimensional space, which clearly doesn't actually exist. So why did y'all decide to really focus on these physical real world objects, especially for a show that, say, doesn't even have visuals?
I think it's kind of just an excuse, really, to kind of hang something on a hook. So sometimes we might start with a physical object, but end up talking about something that's really quite abstract. I guess also for me, coming from the viewpoint of someone who is a pure mathematician, I don't really know that much about applied maths. So if I was going to talk about a real world application of maths, that would be kind of slightly outside of my comfort zone. So my favorite thing is to take a real world thing and find the pure maths in it, which I think is quite nice.
There's only probably so many physical mathematical objects that you're going to be able to easily get your hands on without, say, going to great expense and buying a bunch of new stuff for this podcast. So do you have any intentions in the future to maybe stray into a more abstract realm?
Yeah, definitely. So we started the podcast because Katie was going to come and work where I work. And I sort of said, well, we're going to be in the same place, every week. Why don't we do something with that? And Katie said, oh, what about a podcast? And I think we like the challenge of having a physical object that the listener can't see, that you've then got to sort of use that as an opening to the world, even though it's a very visual thing for an audio medium, and somehow that seemed like a good idea. But there's also, I think we both have kind of boxes of stuff that we've accumulated over the years. So it's a bit like, well, here's a bunch of things we can talk about. And at the same time with that, we recognize that mathematical objects as a term could refer to pi is a mathematical object, or, a function is a mathematical object, or whatever it is. So there are opportunities to talk about more abstract things as the base point, and we may do episodes where there isn't a physical object we can hold. But, I mean, so far we've used physical objects. Even then, they sometimes take you to unusual places. Like I mentioned, the noughts and crosses board, which is a wooden toy that I bought in a charity shop for my son, and we sort of play with it. But by talking about noughts and crosses, we quite quickly got onto sort of higher dimensional games and things like that. So there's an opportunity to talk about more abstract mathematical things, even though you're basing it on a physical object.
Yeah, and I should also clarify that I am always happy to take any excuse to buy a new maths thing. Like if there is the possibility of me getting something, that I didn't otherwise have an excuse to buy, then I'm well in for that. But yeah, I think also because the listeners can't actually see the object, it kind of doesn't matter whether it's a real object or not. And we've been trying, for the purposes of the podcast, to have a photograph of the object that we were talking about, but I mean, that won't always be practical. And sometimes, we've just talked about something without it actually being there and then sourced a photograph otherwise. So
no, I mean, that's never happened. There's never been a recording where Katie said, "Gosh, that's lovely," as if she's holding something and it's not really there. No.
I'm pretty sure.
And also sometimes we do the recording, but you've taken the picture, a couple of weeks earlier, and we've just not bothered bringing it. Left the object in my office or something. But
Well, now that we've talked around the idea of this podcast and heard some examples, I think it's probably going to be a good idea to bring in an example, a mathematical object of its own. A mathematical objects podcast. It's getting a little bit meta, but here is one of the episodes all about a shirt.
Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what's today's mathematical object?
Well, today I've stolen a T-shirt from my son. So my parents went on holiday to Greece recently, and they climbed the Acropolis in Athens and went and had a look at the Parthenon. And then the way my mum tells it, coming down the hill from the Parthenon, they went in a shop, and this shop had T-shirts, and they have this T-shirt that shows the Pythagorean theorem, Pythagoras' theorem. And so they bought one for me in grown-up human size, but they also asked whether there was one for my son is 3, he's about to turn 4, and the lady who runs the shop mum said she went into the down some steps into the depths of Athens somewhere and came back with this T-shirt that's really for 5-year-olds and is a bit big on him, but he loves it, so I've nicked it. So why it's a mathematical object is that this being Greece, it shows the Pythagoras theorem. So this is a triangle. The triangle has a right angle, and the way I would say this for the purposes here is that if you've got triangle lengths, I wonder whether to use the letters on the T-shirt.
I think it's got alpha, beta, and gamma.
Yes.
So A, B, and C, I guess.
I know, my notes say A, B, and C, but in a different orientation. But anyway, so if you have B and C being the shorter lengths, and then the big long hypotenuse is A in this case, then you would say if you put a square of side length B and a square of side length C, then the areas of those two squares, if you sum them, give you the area of a square of side length A. And the reason I'm saying it that way is because the period that we're talking about, they didn't have algebra yet. So what you might write, and what's written on the shirt, is a squared equals b squared plus c squared. Nice and straightforward, everybody remembers that. Which sides are A, B and C seem to be up for debate. When I was at school, I was taught O, A and H, opposite, adjacent and hypotenuse. Which
I guess
is
with a
orientatable.
right angle triangle you can define those as unambiguous. Yeah.
Absolutely. Anyway, so I think it's sort of interesting that this famous theorem is always expressed as this bit of algebra, even though it predates algebra. I think that's interesting. And an example triangle is, the classic example is if the two smaller sides are of length 3 and 4, then the squares have area 9 and 16, so then the square on the longer side has area 25 and therefore side length 5. So 3, 4, 5 is an integer solution to this equation. And integer solutions to those equations are Pythagorean triples. What sort of interests me about this is Greek mathematics is said as if it's a thing, but it's sort of not a thing. It's sort of a big mess of different things. And that's true in geography. One thing that I think always surprises people is that Greece is a country nowadays, but Greek mathematics, an awful lot of that happened not in Greece, the modern country.
Yeah.
So Pythagoras was in modern, what we would call Italy now. And I was looking up some other mathematicians. So, sort of, for example, Euclid and Ptolemy are both from Alexandria, which is in Egypt, and Archimedes was in Sicily, and that sort of thing. So you sort of have this idea of Greek mathematics taking place, but really, and Greek mathematics being distinct from Egyptian mathematics that came before it, and Islamic, Arabic mathematics that came after it, but actually a lot of them are in the same actual locations.
Right. Yeah, so it's more of a time thing than a geography thing.
I guess so, or a sort of era thing. Because when we say Greek mathematics, there's a sort of Greek culture that's shared by all these places, but there's also, the thing is the language, that they're all writing in Greek, and then later they're all writing in Arabic, And then after that, the sort of language of science and scholarly communication becomes Latin, and nowadays we would say that was English. But at the same time, if you say Islamic mathematics, you often get people being a little bit annoyed at you because there's nothing religious about the mathematics that's happening, right? And you would sort of say Arabic mathematics, not that everyone involved was an Arab, but that they're all writing in Arabic.
Yeah.
But then for the European Renaissance, you don't call that Latin mathematics because they're all writing in Latin.
Yeah.
And now we wouldn't say English mathematics because we're all writing in English, right? So there's that sort of, geographically, that's sort of interesting, I think. And the other thing is it's very displaced in time. So the very early sort of Greek mathematics, well, for example, some of the early proof techniques were about 600 BC. Pythagoras is 500 BC. Plato, who was actually in Athens, he's an actual Greek, if you like, was about 400 BC. Euclid was about 300 BC. Archimedes was about 200 BC. Even going right through, Diophantus is interesting. So Diophantus wrote a book, and in that book he wrote a page listing Pythagorean triples, going back to Pythagoras' theorem. And that book, or rather a translation of it, is the one that Fermat wrote his note in the margin, which became Fermat's last theorem. So Diophantus is sort of famous for that reason. Well, he was about 200 AD. So that's from 600 BC to 200 AD. There was a bit of stuff going on before that, but even that period is 800 years. Now, if you think about from now, 800 years ago is Fibonacci.
Yeah.
So that's this period when the most scholarly activity is happening in the Islamic world. They're translating Greek texts, Indian texts, they're contributing additionally to those. And then merchants from Italy and places started to get educated by Muslim scholars and then brought some of those techniques into Latin, and Fibonacci wrote this book that was sort of the first mathematical activity for 1,000 years in Europe or something. I think you have to say Europe excluding the bits of Spain that were Islamic at the time. But anyway, so from there to then go through the entire Renaissance, get to people like Newton and calculus and all the modern stuff and everything that's happened, that's 800 years. So that's the sort of span that we're talking about. So people talk about as though Pythagoras knew Euclid and Euclid knew Archimedes, and they all just hung out together in Athens, and it's just nonsense. Anyway.
But I find that really interesting, that the difference between where maths was 800 years ago and now. We've got all of the modern mathematics and all the computer-aided stuff and everything that, a lot of the really abstract pure math stuff. But I guess it also coincides with a major shift in how much of people's time they were able to devote to academic pursuits. Because I guess in the 800 years ago, you still had people who were basically polymaths who were doing all the subjects, and you'd have like a scientist or someone like Da Vinci who's an artist and a mathematician, who they're not just researching maths full time.
That's true.
But,
they also didn't have television and
I guess there's a lot less to distract you. But
because there's this whole thing that people a few hundred years ago would calculate things to ridiculous numbers of decimal places by hand and do all these really elaborate, complicated things that you just think, you wouldn't bother now, you just put it in a calculator.
And maybe that also has contributed to this kind of exponential growth of progress. But it's true in all kind of science research, I guess, that now that we've got these tools, that it suddenly just opens up massively what you can do with it. Yeah. But it did take 800 years to get from the start of ancient Greek maths to the end of it.
Yeah. Anyway, so then you get to interesting questions, and one of which is, did Pythagoras exist? So the thing about Pythagoras is, everybody knows he existed because they all learned about Pythagoras' theorem, and that's that.
There's a T-shirt.
There's a T-shirt.
Yeah.
Yep. That's all fine. We have nothing, I believe, that Pythagoras wrote.
Right.
And that's not unusual for Greek mathematics because they wrote on papyrus and a lot of it perished. And so the reason that we know so much about Greek mathematics is because of those Islamic translations that then got translated into Latin, and that's how we have a lot of these texts. But the earliest accounts we have for Pythagoras were written after his death, attribute him with divine powers.
Right.
Disagree on dates by sort of decades in some cases. And some of the earliest ones we have are very brief. and then more detail gets added. So there are a couple of hundred years after he died that give a lot more detail than the earlier ones. Now, that might mean that there were earlier ones and we've just lost them. This is one of the problems with studying history, is you don't really know what you don't know. So you might have lost documents along the way. But there's other stuff going on. Pythagoras was essentially a cult leader. He founded a school called the Pythagoreans, which lasted for several generations and had some very odd rules. So kind of what you're talking about is people a couple of hundred years later writing about the founder of their cult, their religion or whatever. And you can sort of imagine that might not have been the most accurate thing. And one thing I think about is, for example, if you found a text now about King Arthur, hundreds of years ago, has divine powers, would you believe that was true or not? And the one I often use is Robin Hood, because I'm from Nottingham, and Robin Hood is one of these characters that if all your evidence all the evidence that you had was a sort of late 20th century book about Robin Hood, would you be able to tell whether that was accurate or whether that was a real person or not? It's ever so hard with the timescales that are involved. One thing we do know is, so the theorem itself, there is evidence of its use in Mesopotamia on clay tablets, which don't perish, like papyrus does, sort of 1,000 years earlier than Pythagoras was supposed to have lived.
Right.
So the theorem was being used long before he existed, if he existed. Now, it might be that he was the first to prove it, and there's this notion that in mathematics you name things after the person who proved it. I did mention Fermat's last theorem earlier, which we might call Fermat's last conjecture, or Wiles' theorem, but we don't, because it was already famous before it was proved. But in general, you often name things after the person who proved them. Now, was this going on then? Who knows? Or maybe one of the Pythagoreans proved it. I mean, it's just so hard to know, isn't it? You can sort of invent scenarios. I heard a talk once from somebody talking about all this sort of stuff with the timescales and things, and he said, for all we know, Pythagoras might have been a baker, and they set up shop next to the baker's, and it was the cult of the people who live next door to Pythagoras, and over hundreds of years that gets translated. But I mean, you just don't know. It's sort of nonsense, but it's sort of not, and I just find that quite fascinating. So the Greeks, we think, originated mathematical proof, and so it might be that the proof of this theorem came then. Certainly it was in use before. Very hard to know what's going on. But I think that's all very interesting about history.
Yeah. Is there a thing about Plimpton 322, like this sort of tablet that was found with Pythagorean triples on?
Yes.
Completely out of time compared to when we thought it was known.
That one has Pythagorean triples on. The other one is, there's one which I can't remember the name of, and it's a code, YB something or other, which has on it a square, and then the square has diagonals across it, and one of the diagonals is labelled with a very good approximation for the square root of 2.
Right.
So if this square was a unit square, then the side lengths in the terms that we were talking about would be b equals 1 and c equals 1, and then a would be the square of 1 plus the square of 1 square rooted, which would be the square root of 2. So it's in ancient Babylonian mathematics, so they had a sort of base 60 system. So it's a bit complicated to work out, but when you work out what this notation is saying, it's the square root of 2 to quite a lot of decimal places. So that's a good evidence that they knew about this theorem, because otherwise how are you working out the length of this diagonal?
Well, unless it was just incredibly accurate measuring.
Yes, quite a lot of decimal places, yeah. The reason I know about that tablet is, I have it in my history of maths lectures, but also at the Maths Jam annual conference has a baking competition, and I made gingerbread version of this clay tablet for last year's baking competition at the Maths Jam conference. So I found a recipe online that I saw somebody tweet about that was for making gingerbread that you can put cuneiform writing in with the end of a chopstick. So that's what I did, and I sort of practiced a few times, and I baked this thing, and I think it came out quite nicely.
Yeah, I remember there was a couple of years ago there was a bit of a news thing about the Plimpton 322 thing, because there was someone I think had come up with a new theory, new in finger quotes, that it was that the reason that they had this massive list of Pythagorean triples was because they actually knew a better, or they had a version of Pythagoras' theorem decades or centuries before Pythagoras. And it was really interesting because at the time I was asked to come and talk about it on the radio, and I was kind of on the train to somewhere, and I had to find somewhere to go and talk to them when I got there and that kind of thing. And I was just sort of frantically looking at what is this thing?
Right.
What's this person actually theorised?
Because there's a thing that people on the radio do where they sort of go, we need an expert. This is maths. This person is a mathemaician. They'll know about it. Right?
Well, I quite happily went on there and explained what Pythagorean triples are and how all of this stuff is worked out. But I couldn't quite see how what this person had done was actually new,
right,
or whether they'd just wildly conjectured, that this might have been a way that you could have done it.
Yes.
And it was so difficult to sort of go on there and say, well, it's interesting that this person has wildly conjectured these things because they don't have any actual knowledge of what was really going on. But this is the problem with history, is that you can only use the evidence you've got.
Yeah.
But, I mean, I guess to some extent that's science, isn't it? You make some physical observations about the world and then you conjecture why that's happening as a sort of theory. But yeah,
it is. But you also have flawed evidence in history.
Yes.
So you have people with their own agenda writing these things, and also there's the influence of folklore, because it's a lovely story that all the stories about the Pythagoreans that there are, they're good fun to tell as stories. Whether they actually happened or not is, sort of so what, because they're part of the culture of being in mathematics, that you sort of tell these stories to enlighten, enrich your lectures or whatever it is.
Yeah, well, it's one of the things about maths as a subject is that you can learn all of these things without any of this historical context at all. You can just learn about how the equation works. But I think knowing that there's this human aspect to it makes it so much richer as a subject.
Definitely.
So, really, Peter, the shirt off of your own son's back, was he just running around shirtless the whole day so you could make a podcast?
The worst thing is, I think I took it into the office intending that we would record it, and then for some reason we couldn't record that day, so it just sat on my desk for a week. But he didn't seem to notice. He has enough Star Wars t-shirts to keep him in t-shirts, don't you worry.
So there's a lot of really interesting things that, a shirt brought out, which really shows sort of how this idea of having an object and then talking around it can help out. Specifically, the talk that you had about the huge gap in Greek math, so that what they accomplished took them about as long as developing the entirety of modern mathematics, I found to be fascinating. And it was something that I had never thought of before, even though I think about math all the time.
Yeah, I think people are sort of aware of dates and how numbers work and things like that, but don't really think about it in that way. And so putting in expansive time and relating it to something you're more familiar with, I think can be quite powerful in that way. Yeah, I like how you can get to a lot of information from an object, because partly what was in my mind when we were first talking about this was a few years ago the BBC did a radio show that I listened to as a podcast with the British Museum that was called History of the World in 100 Objects. And that was 100 objects that sort of illustrate a topic that you want to talk about. And more recently, Tim Harford and the BBC have done a series called 50 Things That Made the Modern Economy, I think, which is an economics show. But again, it's not just literally that object or that thing in that case that they're talking about. It gives you a window into a topic and something tangible to go in with. So that's what I felt about this t-shirt. I thought, well, I know I have a bunch of stuff from teaching first year history of mathematics. I know I have a bunch of stuff about Pythagoras and how you measure evidence from the past, and also some information about Greek and later mathematics. And I thought, this t-shirt is a really good way into that topic.
Yeah, and I think it's been nice for me, actually, because there are various things that I've spent time researching or reading up on because I had to do like a 5-minute talk in a variety show sometime several months ago. So all this stuff is kind of in my head. And this has been a really nice excuse to pull bits of it out and share it with people, I think, because it's that thing in my line of work, you end up using the same content in several different forms. And I might write a blog post about it, or I might, do a bit of a podcast or do a bit on stage or produce a YouTube video. And I can do that with everything. I can do all of those things if I wanted to, but there's a lot of them I've kind of used for one or one and a half things and then never really used again. So it's also nice to pull that out. But at the same time, it's also got me interested in and learning about lots of new bits of maths that I didn't already know about.
Another interesting side that you brought out in this episode was sort of the Pythagoras person or myth thing, sort of covering how we don't really know that much about the truth of Pythagoras. But one thing I wanted to say that you didn't mention that is one of my favorite stories is about this sort of craziness around the person who first used the Pythagorean theorem to prove that the square root of 2 was irrational, which violates the Pythagorean cult's belief in sort of the beauty of the rationality of numbers, and how that perhaps led to them either banishing or killing this poor person. And so why did you leave out my favorite story?
Well, that's the sort of story that you hear, isn't it? And that's what I was trying to touch on with the difference between historical accuracy and folklore. Because this is something that I teach first year history of mathematics, but there's a way of teaching history of mathematics where I would just stand at the front and tell stories from history to my students, and they would listen and learn some facts and do an exam and all that sort of thing. But I think what's really interesting is this opportunity to develop sort of critical thinking and think about how do we know that something happened in the past, and not for me to kind of hide that from my students and just present my version of what I think happened, but to expose them to that uncertainty. And one of the things that we talk about is historical inaccuracy. I have a lecture where I talk about, there's a famous book by E.T. Bell called Men of Mathematics, which has a lot of semi-fictionalized stories about mathematicians in it, but it's a very inspirational book to a whole generation of mathematicians. And it's trying to get to that nuance of, this story might not be accurate, but it might be one of the stories that mathematicians tell each other that's actually an interesting part of folklore. And I think some of these Pythagorean stories are like that. They're kind of nice stories, but whether we treat them as evidence in a historical sense is very hard to say.
Yeah, I guess that story's always made me feel like the thing about irrational numbers is they are a bit weird. Like, they're not quite the way you expect numbers to behave. And that kind of the idea that someone who first proposed this would get, chucked off a cliff or whatever is kind of nice, because it makes you feel like when you're using those numbers, you're like, well, this is a special thing.
And it's really useful for students who, at whatever stage of education, who are struggling. If you can say at some point in the past, the greatest minds in mathematics really struggled with this concept. And of course, you're also now struggling with it, but that's fine, because at some point that was world-class minds were also struggling with this, and you're only sort of learning it in school or whatever. That can be quite inspirational in terms of sometimes it's okay to find things difficult or to find concepts hard to deal with.
Okay, we'll just gloss over Katie there saying that it was kind of cool that they killed somebody over numbers and head right on into the next episode. So this first one was driven by something that Peter brought in, and this next one is driven by something that Katie had brought in, and it's something very near and dear to my heart, citrus.
Hello, I'm Katie Steckles.
And I'm Peter Rowlett. And Katie, what's today's mathematical object?
Today's mathematical object is a tangerine.
It's another in this line of things that don't appear mathematical but secretly are.
Yes.
Good.
I think I've kind of found a nice piece of maths within a tangerine. So the origin of this is that when I was a kid, my dad always used to do amusing things like peel fruit in a funny way and things like this. And I have a very strong memory of him explaining the theory of plate tectonics using an apple. And he just sort of cut pieces of peel off the surface of the apple and explained that they can move around a little bit, which is really nice. Although that's very much not how plate tectonics works. The apple would need to be a liquid, I guess. But anyway, one of the other things he would do is he'd peel a tangerine just by hand in one go. So you end up with a single piece of peel at the end of it. And there's obviously a bunch of different ways to do this. I think there's a way that I've seen done that you end up with something that looks a bit like an elephant. I can't remember, you kind of take two ears off the sides and the trunk from underneath and something else. But the way that my dad used to do it was in a spiral. And he'd start from the top of the tangerine and kind of spiral around and keep going all the way around until the bottom of the tangerine. And this is lovely, and you end up with one piece of peel. But kind of, I always imagined it as being one long strip of peel, and I never really thought about what shape you actually get. And if you do this, it turns out if you peel it from the top, spiral all the way around in the same direction until you get to the bottom, you end up with, it looks kind of like an S shape or like an integral shape. It's kind of a curve that changes direction in the middle. And it's strange because I'd always thought of it as being a straight strip of peel, but it's got a very distinct curve to it.
It's a sort of thin strip, right? It's
Yeah.
a sort of how thin, sort of a centimetre thin strip.
Yeah, well, I guess you can vary the thickness of it, and depending on how thick it is, you'll get slightly different results. But in general, they'll all have this same kind of basic shape.
Because I'm imagining, if you look at a globe being put onto a map, you often get this where it's sort of sections that have been cut off together that are all joined up, but it's a bit, and there are map projections that kind of twist that to make it fill a rectangle and not fill a rectangle and things like that. And like you say, you can do all sorts of other odd shapes where you make several cuts but don't ever quite disconnect them, so it all comes off in one piece. But this is literally just the same motion right from the top. You're making a thin strip going round and round and round all the way down to the bottom.
Yeah. And it turns out, because I only recently kind of investigated properly what this was, I've always done this. Like, every time I've been given a tangerine in my entire life, I've always peeled it this way. I've realised I've just given the impression that I've never bought myself a tangerine and I'm just like a child wandering around being handed fruit. But any time I have obtained a tangerine by any means, this is the way I've peeled it. And I always do it just without even thinking about it. And people around me go, oh, wow, that's really nice.
Yeah.
Or they're impressed that I've managed to do it without snapping it anywhere.
Well, that's true, because it looks like it's going to break somewhere, but it is a pretty thing, and you don't expect it.
And it's not the shape you would expect to get. So I thought, I wonder if there is a mathematical reason for this, and I started to dig into it. And I found a paper that someone's done where they've properly explained why you get the shape you get. And the paper is called something like Orange Peels and Fresnel Integrals, which is a magnificent title for a paper. And it includes it's a photograph of a peel that they've done of a full-size orange, so it's quite a decent amount of peel, and they've used a knife, and the strip is about 2 millimetres wide, and it's this beautiful, intricate object that they've created. But I guess the theory is that the shape you get, the thinner strip you take, the better approximation of the shape it is. So if you've got a really wide strip, you might just get sort of a curl at one end and a curl at the other end.
Like a proper integral sign.
Yeah, like an integral sign. But then if you have a thinner strip, you'll have more kind of winds at each end. So the theory is, if you start at the top of the tangerine, or the sphere, as I'm probably going to end up referring to it because that's what it is.
Start at the North Pole.
Start at the North Pole
right?
of the tangerine. And you start off with a very tight curl because you're basically just going straight back on yourself because you're working on the top surface and it's basically horizontal. I mean, there's going to be a lot of basically here because I'm basically using a manifold, right? I'm modelling this as a manifold. So locally at the top, it's horizontal. And then
if you scalped the tangerine and just did it to that bit, you would just get a little spiral.
Yeah, you just get a little internal spiral. So then once you get outside that bit, it starts to get bigger loops. And as you start going down the side of the tangerine, the curve gets looser, I guess is the correct term. And it keeps continuing to get less curved. So it's straighter and straighter until you get to the equator of the tangerine, right. Which the tangerine now has a North Pole and an equator. It's still not the Earth; it's still just a tangerine. Yep. But it's basically a straight line when you get to the equator, and then beyond that point, you continue spiraling in the same direction around the tangerine. You don't stop and change direction at any point, so you're going the same way. But instead of it now curving outwards, it's now curving inwards again. It's sort of tucking underneath. So the curve that you've got, it goes from being curved very much at the top of the tangerine, increasingly less curved, or decreasingly curved, as you get towards the middle, where it's zero curved, because it's a straight line. It then starts to curve the other way, gradually, and then gets more and more curved until you reach the South Pole, where it's a very tight spiral again. Mm-hmm. And I guess in the limit of this, when you've got an infinitely thin strip of peel, it's an infinite spiral at the end. It kind of never finishes. It just sort of ends up at a point or whatever.
And it's completely symmetric, as a sphere is symmetric.
I think so, yeah. Depending on how symmetrical your tangerine is and how good your peeling skills are.
Peeling, right.
You get something that is, in theory, rotationally symmetric. And it's a really lovely shape, and it's called an Euler spiral. Named after Euler, who all the things are named after.
Because Euler peeled a tangerine this way.
I assume so, yeah. Yeah, I never know with things whether it's named after Euler because Euler did it or because someone just went, you know who's great? Right. Let's just name this after Euler. Yes. Anyway, the Euler spiral, I suspect it is because it ties into a lot of nice sort of physicsy things that Euler feels like Euler might have been involved in somehow. But it's a curve whose curvature varies with the distance along the curve, basically. So at the middle of the curve, the curvature is zero, and at the ends of the curves, it's plus and minus infinity, basically. So if it's positive curvature, it curves one way, and if it's negative, it curves the other way. And it's a known structure. And it's really lovely that just because this fruit happens to be a sphere and I happen to peel it in a way that's got some kind of logical ordering to it, that I get this wonderful known shape. And it has a couple of sort of applications. So I think it's the kind of curve that you use if you want to design something like a railway line, or if you're a racing driver picking a line on a racetrack, because you don't want to accelerate like turning wise accelerate. I don't know how you separate out speed acceleration versus direction acceleration.
Comfortable with it being a vector?
Yeah, but okay, it's a vector, fine. So you don't want to accelerate too quickly.
Mm-hmm.
So you want the amount of turning that you're doing to change constantly or change in a linear way. So
because if you're a train or a tram or something, I'm remembering they put a tram in Nottingham. There's a big curve in the market square, and when they first opened it, they had a lot of trouble trying to get trams going around this without falling off the tracks at some point.
Yeah.
And that's to do with it basically was turning a little bit too sharply, I think.
Yeah, so if you use a section of an Euler spiral, so if you want to go from straight to curved, you need to start with zero curvature and then gradually increase the amount of curvature as you go around, sort of thing. So they'll use sections of this curve to design railway lines and things like that. And then there's also, I think there's something else, something like the distance between 2 points on an Euler spiral can be used to model the amount of the rate of drop-off of light passing through a slit or something in optics, that if you shine some light through a thing, the rate at which the light drops off once you get past the slit is modelled by the distance between 2 points on an Euler spiral. So it connects into lots of other different areas of maths, but it's just a really nice shape to look at. As you say, when you see someone do this, they put it down on the table and you go, oh wow, that's lovely. But it's got all of this kind of nice maths behind it.
So what is happening to the curvature? That's what I'm... So as you go along this thing, the rate changes...
Oh, it's going to be one of these things, isn't it? I think it changes linearly with the distance along the curve, I guess. Okay. So
there's really a family of them, I suppose.
Yes, I suspect so, yeah,
rates,
depending on the... I mean, I was going to say on the curvature of your sphere, but that's all spheres, isn't it? I mean... Yeah, I'm trying to think how the family would be parameterized. I don't know. I guess it might be the thickness of the strip of peel or something like that.
Yeah.
But you might find the center line of the strip is a slightly different version of the Euler spiral each time or something. But it's also referred to as a clothoid, I think is another name for it. Some people I've shown it to have said, oh, it's a clothoid.
Okay.
It was particularly when I was in the Netherlands. Everyone, oh yes, clothoid.
Right.
And I was like, is that just what you call it here? Or is that another name for it? Because there are other things that are also called a clothoid. I've definitely seen Hugh Hunt describe the loop on a roller coaster shape as a clothoid. Okay. So I don't know if they're related or if that's just another thing that uses the same word. But it's... it's the curvature is dependent on the distance along the curve in a linear way.
Okay. And I'm sort of getting Euler, because the exponential function, the rate of change is determined by the current value, and it sort of feels a little bit that sort of, but it's not quite that.
Yeah, maybe that's the connection. I don't know.
Maybe. And then you've got an asymptote at the 2 poles, basically.
Yeah. Or a little stem on your tangerine. That's also known as an asymptote. Yeah.
Yes.
And the dot at the bottom, don't know what that's for.
No. But clearly, and also an asymptote. Yeah.
Yeah. But the best thing about the Euler spiral is that there is a free one included with every tangerine.
Absolutely.
So whenever you get any kind of peelable fruit, I should say this also applies to satsumas, mandarins, clementines, the whole range.
Yeah. So you can play around with this spiral without having to strip the surface of the earth.
Exactly, yeah. I did do this once as a live demo, and I asked someone to fetch me some peelable fruit. Just any kind of peelable fruit is fine. Right. And they came back with a blood orange. Oh. And I ended up doing it by hand, and I had to dig my thumbnail into this thing. It was absolute murder, and at the end of it was all juice under my thumbnail, and it was horrible, but I had to do it while talking to an audience. So I kept it together, but only just. But I did get to eat a delicious blood orange afterwards. So that's the other benefit to this as a demo, is you get a fruit that you can then consume afterwards.
That one is really interesting to contrast with the first episode that we heard, because that first one, we ended up spending a lot of time talking about history and sort of mathematics that a lot of people will have learned about. And on this one, we ended up going into some legitimately pretty deep math, and even a paper was mentioned. So how do you sort of see balancing those two different methods of driving the conversations?
I think, it was a topic that this is one of my absolute favourite bits of maths I've recently kind of had a play with. And it was a topic that I genuinely was looking for something interesting to do on stage. So I do a bit on stage that involves peeling a tangerine while talking about all of this stuff. And I needed something to kind of back up what I was saying, because I thought there must be something interesting about this. I know I can make this shape, but what is this shape and where does it come from? And in kind of digging around it, I found all these bits of papers and research that people had done. So I guess if you're talking about any maths topic, it's good to have some kind of backup if it's, actual kind of maths content. And I guess with the historical stuff, there'll be historical research papers that Peter's had a look at for various, bits of his course. But yeah, I don't think we're claiming in any of this to have actual authority, and a lot of this is just opinion and things that we think are neat and interesting, some of which may or may not even be true, but we're just, telling stories, I guess. But yeah, I think for that one, it was really nice to see that I wasn't the first person to have asked that question, and to find actual mathematicians had done a paper on it was really nice.
I found this absolutely fab because it's just this thing that you were doing at lunch and you were like, oh, I could do this as an object or something. And just like this, I had no idea about this at all. But also what I like about it is when we put it out, someone replied and said, if it doesn't have the sine gerene over cos gerene joke in it, then something's gone terribly wrong. And I like that what we think is an object and a way into a topic, for somebody else that object might inspire a completely different thing, and they were going down a sort of maths jokes route with it, which I thought was quite interesting.
I mean, maybe there's a podcast in that in future as well, like on whatever the classic mathematical jokes are, like an abelian grape. I don't know.
So there was there was, sort of a side of it that I also pulled out just to go, and that there's an infinite number of ways of approaching this, and that's the tool that they use to do citrus garnishes. It's this little dig out tool that they use to pull these very thin strips that end up forming the same shape out of, say, orange peels when they are garnishing drinks. And it's this really weird tool, and you can actually use it to make multiple versions of the same curve from the same piece of fruit.
Oh, that's amazing. Yeah. Like a super zester. I don't know. Yeah.
And also I want to thank you for one thing about this episode, in that I eat a lot of citrus. Now, not primarily tangerines. I primarily eat oranges, where it's a really significantly harder, as you mentioned with blood oranges, to peel in this way. But now I am never, ever, ever going to be able to get out of my head that a citrus stem is just an asymptote.
Yeah, I found sometimes when I was trying to explain this kind of thing that I would be referring to like the North Pole of the orange or the tangerine. And like that's completely mixed metaphors, but it helps people a lot to think of it as like the North Pole and the South Pole and like the equator of a tangerine. I don't know if that's a concept that's been thought about heavily before, but.
Well, before we head out, is there any chance you might be able to tease the listeners with a few of the upcoming mathematical objects that might be on the table, so that they will definitely 100% go into their podcatcher of choice and subscribe to mathematical objects?
Yeah, so we think we're going to release sort of 8 at the moment, and then take a break over the summer, and then another 8 in the autumn. We had a few that we've released already, are things like, there's some really classic things like Towers of Hanoi, and we had one where I did a pile of matchsticks and we talked about NIM and NIM-like games. But there are some quite out there ones as well, like a colleague of ours at Sheffield Hallam University, Alex Corner, came onto an episode, and we did this one where he takes tiles from the game Tantrix and relates those to a piece of graph theory called beaded necklaces, and then relates those into juggling patterns and talked about juggling balls. And that was just a really nice story of lots of different things linking together in a way that you don't think. And we also had one where Katie brought a stick of chalk and tried to convince me that chalk was better than whiteboards for teaching. So we talked a lot about teaching in that episode. Some of the upcoming ones we've recorded, I don't know if we've decided on an order, but we've things like a deck of set cards. You might know about set cards. Katie has a thing about pseudo-rhombicubo. How do you say that, Katie?
The pseudo-rhombicube octahedron, of course.
Of course. Silly me. And there's some things like we have one where we talk about mathematical modelling based on a thermometer, one with a pair of skipping ropes, which is a little bit of topology, I think. But the conceit for the show is that we've sort of huddled away in a classroom that nobody's using, and we're quickly recording this episode. And that is literally true.
Yeah.
So we have one recording, which is sort of half an episode about a Klein bottle, and then somebody came in and we had to leave the room. So at some point we need to finish that one off.
I'd forgotten we hadn't done that. Yeah.
But I think we're going to release another 1 or 2 at the moment, and then save the rest for the autumn. That's the plan.
So you have all of these objects, but is there any way for perhaps listeners to become involved at all and in the objects that might be coming up that they want to listen to themselves?
Well, we've set up an email address, objects@aperiodical.com, which we mention at the end of every episode. So far, I think we've had 0 emails to that email address. Most of the response we've had has been on Twitter, and I think people are quite often responding and replying to things. And we also say, if you have an object that you think we should talk about, then suggest it, and we'll have a go at doing that in a future episode. And we have actually done one as well, I think we recorded but haven't released yet, about a Romanesco broccoli, which is the sort of cool fractally broccoli. And that was just a nice excuse to chat about fractals and various fractal related topics, but also to think about kind of why that happens with plants and that kind of thing, using my extensive lack of knowledge of biology. So that was quite a fun one. And I guess if other people have ideas for things, we've had a few other suggestions in that we haven't had a chance to do yet as well. So please keep sending them in and we'll see what we can manage.
Hey, well, everyone should definitely go and subscribe. I'm very happy that there's another really fun mathematical podcast out there. So, Peter, Katie, thank you so much for coming on Relatively Prime, and thank you for making mathematical objects.
Thank you.
Cool, thanks.
And that is all the time that we have for this episode of Relatively Prime. I want to thank Peter and Katie so much for agreeing to be on this episode of Relatively Prime. You can find them on the internet at theaperiodical.com or on Twitter at Steckles and at Peter Rowlett, respectively. The music that you've heard on this episode, both in the Mathematical Objects episodes as well as on here, is Funk Game Loop by Kevin MacLeod. You can find over at filmmusic.io. And of course, I want to thank, as always, all my patrons from Patreon. This show could never and will never be possible without you. And a big shout out to my friend Inez, whose kitchen I am currently recording this in while I'm on vacation. Thank you so much, Inez, for giving me the space to do this. Relatively Prime is, as always, brought to you under a Creative Commons license, so please feel free to share it around as long as you say that you got the sounds from Relatively Prime. Thank you all so much for listening, and, as always, have a matherific week.